Okay, so we're going to do a slightly different type of induction proof. It's actually less work. It's just a little tricky to see at first what it is that we have to do exactly, okay? But it's the same principle. Okay, so this is just more induction proofs. Here's an example. Let's say we wanted to prove that 5 divides n to the 5th minus n for all integers n greater than or equal to 2. Okay? Now, we haven't seen this yet, but just so that everybody's okay with the notation, 5 divides n to the 5th minus n can also be written as 5 and then this like vertical line. So if you see that 5 and then a vertical line, that means exactly the same thing. 5 divides n to the 5th minus n. What does it mean for a number to divide another number? Edward? Yeah, there's no remainder. So, for example, 5 would divide what numbers?
25.
25?
5.
20, 5, 10. What about 0?
Sometimes.
Not sometimes. Does 5 go into 0?
Yep.
Yes.
0 times.
Exactly 0 times, right? Trick
well,
question.
For here, you can't use that, right? This is any integers above greater than or equal to 2.
Well, that means in this part of the formula.
Oh, okay.
Yeah. Okay, so start with the same exact format. Basis step.
Wait, we can't do n equals 1, right?
We can't do n equals 1, right, because it says 2 or more. So what's the first case here?
2.
So that's the only thing that changes so far. So for n equals 2, the statement really is saying now that 5 divides what? 2 to the 5th minus 2.
Which is 2.
5,
Over
2 to the 5th is 32.
2. Oh.
Minus 2 is 30. Does 5 divide 30?
6.
Absolutely, because 5, since 30 equals 5 times 6, absolutely it does. Okay? There's no remainder, right? Everybody okay with the basis step? Okay. So now, the inductive step looks something like this. Suppose that, what? 5 divides k to the 5th minus k. So nothing's changed, right? It's still the same principles that we were using before. What are we going to show? We will show that not only does 5 divide k to the 5th minus k, but also 5 will divide k plus 1 to the 5th minus the quantity k plus 1. Okay? All right. Well, let's see what happens. I don't know about the right-hand side yet, but you know how we always end up using, at some point we need to use this, right? Like in the other problems, we always plugged in or substituted a lot of the equation with the hypothesis. We're going to do that still. It's just we don't know where that's going to come in yet. Because do you see a k to the 5th minus k over here yet? Not yet. So we're going to have to multiply this out and combine some like terms and see what we have, okay? So let's figure out the right-hand side. So it's a little different because we're starting with the right-hand side because that's where everything is. K plus 1 squared, k plus 1 squared, k plus 1. Is that everybody okay with that? I'm just splitting it up to make the multiplication easier. That's still k plus 1 to the 5, right? Well, order of operations. I can't just subtract those. It'd be nice, but can't do that. K plus 1 squared is k squared plus 2k plus 1, and that's the same with the second one. Well, same question Ryan asked earlier. I can't just get rid of it because it's connected with multiplication first, right? Let's multiply these two out. So that's going to be k to the 4. So now I'm just distributing k squared plus 2k cubed plus k squared. Now I distribute the 2k. So that's plus 2k cubed plus 4k squared plus 2k plus, now I distribute the 1, k squared plus 2k plus 1. Let's combine that. That's still multiplied with k plus 1, and then minus the k plus 1. Let me start over here to get some more space. Let's see what like terms we have. We have k to the 4. Any others? Nope. What about cubes? Plus 4k cubed. 6k squared? Okay. Plus 4k? Plus 1? Okay, thank you. That's still times k plus 1 minus k plus 1. Okay, so one more annoying... I hope you're annoyed, because there's going to be an easy way to do this after the next section. Distribute k to the 4 to k plus 1. So now we get k to the 5 plus k to the 4. Distribute 4k cubed. We get 4k to the 4 plus 4k cubed. Now we distribute 6k squared, so 6k cubed plus 6k squared. Distribute 4k, 4k squared plus 4k. Distribute the 1, so that's just k plus 1. And if it's alright with you, I'm going to distribute this negative now, because I'm going to just combine all the like terms. So that'll be minus k minus 1. Alright, let's combine everything I got. K to the 5 is the only one that's to the 5th. What about k to the 4? There's 5 of them? Okay. Plus 10k cubed, 10k squared, 5k, and then minus k. So that's 4k. Yeah, because I forgot to subtract this one, and the ones cancel out. Okay. We're good, right? Okay, so now here's what we have. At some point, I need to have this, right? I don't really... You okay there? That was an interesting yelp. I don't see that anywhere. I see a k to the 5. Do we see a minus k? We did, didn't we? Well, here's what we can do. Let's write k to the 5 minus k. Let's just put that together. And leave everything else the way it was. So plus 5k to the 4 plus 10k cubed plus 10k squared,
Plus 3K.
not plus 3, plus 5k.
5.
Because negative k and positive 5k is still 4k. In fact, that's what it was before I decided to combine the negative k. Did you see that? Right here, this was the 5k, right? And then the minus k was still there, so really, it's... No, because the 1's canceled. Okay, so now, what's our job here? We need to prove that 5 divides all of this. Because if it divides all of that, that's the end of the proof. Well, I know for a fact that 5 divides k to the 5th minus k. Why? Yeah. Right back here, that was the first thing we did, was suppose that 5 divides k to the 5th minus k, right? So this first part of the expression is okay. Does 5 go into all of these?
Yep.
Why?
Oh,
They're all multiples of 5. So if I factored out, for instance, factored out of 5, we get k to the 4 plus 2k squared plus 2k, I'm sorry, cubed, plus 2k squared plus k. 5 definitely divides 5 times all of that, because it's a multiple of 5. Therefore, five divides the whole thing. Which was originally that. Okay? So we're done. Conclusion. 5 divides n to the 5th minus n for integers n greater or equal to 2. To prove that 5 divided n to the 5th minus n was the point.
But you told us that.
No, we were proving that. You didn't know that.
You told us you're never going to give us anything. You can't prove us anything.
Right, but the exercise is to actually do the work to show that you understand why. Yes?
How could you from like the first sheet, from the K to the 5th, keep up a little bit from the, no, like the bottom of the top page.
Oh, here?
No, no,
Up
the
the top
bottom,
page?
first, like,
From here to here?
yeah, how'd you,
Okay. There's two ways to explain this. One, go ahead. One, we had 4k plus k right here, which was 5k, and I just moved the minus k over here. Okay, or if you don't buy that, let's say we combine everything and we have 4k, okay? We need, at some point, we have to see a k to the 5th minus k, because we know that 5 goes into that. Well, if I have it written like this, I don't see that anywhere. So what I did is inserted it right here next to the k to the 5 minus k, but then I would have to add another k at the end, so a minus k and positive k still balance the equation. So that's why this 4 became a 5. So a couple ways to explain that.
So why'd you only change the 4K to the 5K?
Because the only thing I did differently was wrote minus k. I didn't change any other. So then I have to add k to keep things balanced. Okay? We got out of here at what time?
40.
Okay.
Yes.
Last one. Okay, this is probably more like the first ones. It's just a little bit more Actually, it's not that involved. It just deals with exponents, so that can get a little tricky. Prove that 1 plus 3 over 2 plus 5 over 2 squared plus 7 over 2 cubed, etc. And if you don't see where they're getting these numbers from, they tell you what the pattern is right here. 2n minus 1 over 2 to the n minus 1. And the shortcut for that, we're trying to prove that it's equal to 6 minus 2n plus 3 over 2 to the n minus 1. So it's basically like the odds over 2 to the 0, 2 to the 1, 2 to the 2. You see, guys see the pattern there? Okay. They're not weird. They're just odd numbers. 1, 3, 5, 7. And then the bottom is just 2 to the 0, 2 to the 1, 2 to the 2, 2 to the third. Nothing strange here. And let's pretend that you were scared and terrified. It's okay, because it's you're still doing the same 3 steps. It doesn't matter. Okay, so what's the basis step? For n equals 1, what's the left-hand side? Left-hand side is just the first term, 1. Okay? The right-hand side would be 6 minus 2 times 1 plus 3 over 2 to the 0, right? So that's really 6 minus 5 over 1, which is 1. Okay? It works. It always works. If it doesn't work, you messed up. The inductive step suppose that what? 1 plus 3 over 2 plus 5 over 2 squared, etc. plus 2k minus 1 over 2 to the k minus 1 equals what? 6 minus
2k.
Yep.
Over 2 to the k minus 1.
Good. So there's our inductive step. And now here's where you got to plug k plus 1 in. So let's see. We will prove that 1 plus 3 over 2 plus 5 over 2 squared, etc. So I'm just copying what I have up here for the left-hand side, but now I have to add in the next term. The next term, the k's become k plus 1 okay, and on the right-hand side, that'll be 6 minus 2 times the quantity, k plus 1 plus 3 over 2 to the k plus 1 minus 1. Now, if you want to make things a little easier, do you guys want to clean it up? Let's clean everything up so that it's not all weird looking. So this is the same as showing that 1 plus 3 over 2 plus 5 over 2 squared, etc. So now if I clean up this numerator, 2k plus 2 minus 1 really is 2k plus 1. And what's the denominator? 2 to the k. You guys see that, right? And now on the right side, I'm just going to clean that up as much as possible. 6 minus, if I distribute 2k plus 2, that's a 2k plus 5, right? Over 2 to the k. Okay. So,
How come it's 2k plus 1?
where?
If you get it 2k plus 1 minus 1, wouldn't it just be
2k plus 2. Remember, you got to distribute the 2 to both terms. Does that make sense? Okay. All right, so now let's take the left-hand side and substitute what I can. Again, I'll use the red marker. From here to here, we have a formula for that, right? It's right up here. What does that equal?
6.
6 minus 2k plus 3 over 2 to the k minus 1. That's the first part. But I still have that last term. 2k plus 1 over 2 to the k. Bless you. Okay, so again, I'm just going to play the game of how can I make this turn into that. Do I want the 6 here? Yes. What kind of denominator do I want the other thing to have? A 2 to the k. So this one is pretty good. This one, however, a little off. What could I multiply by so that 2 to the k minus 1 turns into just 2 to the k? Just 2.
2 to the 1.
Yeah, 2 to the 1. Very good. If I multiply by 2, because when you multiply, does it make sense that you add exponents, right? So the 2 to the 1, if you need the 1s there to visually see it, you see that the 1 plus k minus 1 would just become 2 to the k, right? And now what do we get up on top here?
4k plus 6.
4k plus 6 plus 2 to the 2k plus 1 over 2 to the k. Okay, so now this is a little weird because they're still not connected. So I'm going to go ahead and distribute this negative here.
Wait, how'd you get rid of that minus 1? Is it because it was 2 to 1?
Yeah.
Okay.
So I'm going to combine everything and just make it addition to start. So this negative gets distributed. I have a negative 4k plus a positive 2k. What do I get? Negative 2k. A negative 6. And then plus 1 is negative 5. Okay. And now, we're almost there. Do you guys see it? Could I just factor out that negative now? 6 minus the quantity, 2k plus 5, all over 2 to the k, and there's the right-hand side. Conclusion. 1 plus 3 over 2 plus 5 over 2 squared, etc. plus 2k minus 1 over 2 to the k minus 1 does in fact equal 6 minus the quantity 2k plus 5 over 2 to the k by induction. Okay?
Is there other ways?
Other ways to what? No.
It's always given by induction.
Yes.
Is there
So do you have to write by induction every time?
No, I mean, it's kind of clear that that's what we're doing, so you don't have to put, just to make the emphasis.